Hello, everybody. Mr. Hinnon here. Sorry for the little delay. I was trying to get things good and ready to go. So, we're going to talk a little bit about rotational kinematics. So, we're going to get into no longer we're not actually talking about like something swinging around in a circle. So, we had our rubber stopper, and I could talk about the rubber stopper swinging around in a circle if I can get it to go around the circle like this. That's circular motion. We had that back in chapter 5, and so that one made sense because it was an object still with some kind of linear motion. Now, what we're talking about is something like this top, where this object, this entire object, is rotating around the circle. So we can talk about this entire object rotating. Or if I take my top here and I spin it, we talk about its rotation. So we're not talking about a single object going around in a circle. We're talking about an object that is actually going to be spinning. So that's what we're dealing with. So in the simplest kind of rotation, like I have our ice skater here, we could talk about different parts. We could talk about their thumb is rotating around that particular point, or their shoulders are rotating, or this thumb is rotating, or their knee could be rotating. So we could talk about an object that's actually rotating at a particular point. So the first thing that we do is we talk about the angle through which it is, and we talk about a thing called angular displacement. Now, the symbol we're going to use for angular displacement is the Greek letter theta. So we're going to stick with something you're probably at least familiar with. And the way they kind of have this here, we have basically a CD or a DVD that's actually spinning, and they talk about it has an axis of rotation. That's going to be important when you're talking about rotational motion. And so they talk about like, oh, initially it's at this point, and then it rotates up to here. So this is the final. So this is almost like an initial and a final angle of the object. And so we talk about the delta, or the change in angular displacement. So that's where this equation kind of comes from. However, I'm going to kind of get into the habit of always starting my initial at an angle of 0. And so I don't really need to worry about delta or theta. So you'll just see me probably use theta for angular displacement. So when a rigid body is going to rotate about a fixed axis and we get this angular displacement, we're talking about the angle that it actually sweeps out. And that gives us the concept of angular displacement. By convention, if something is rotating counterclockwise, we consider that positive, and clockwise is negative. I don't know why that is the case, but that's going to be true. We're going to talk more about this later when we get into the concept of torque and that type of idea. The other thing that's going to throw you off a little bit is we're not going to put angles in degrees. We're going to put angles in radians. So we have to actually have our angles in radians. And the reason why we're going to do that is we also want to relate it to this equation. So our first equation here is, whoops, let's go back for a second. Sorry about that. Give me back my pen. So this is our first equation here, that the angular displacement is equal to the arc length divided by the radius. We actually even already had some videos that dealt with this. So the arc length is the distance on the actual outside, and then the radius of the circle. And that's the true definition of a radian. It is a unitless units. It's kind of weird. It doesn't actually be meters per meter or centimeters per centimeter, but we just give it a name. You are all probably familiar that if something were to go through 360 degrees, that's 2 pi radians. The reason why is because we know the circumference of a circle is 2 pi r. And then if you divide by the radius, the r's cancel out, and ta-da, you've got 2 pi. So key things here. So let's say that you were on the Earth and you were looking at two synchronous satellites that were at this radius, 4.23 times 10 to the 7th meters, and you happen to notice the angular displacement between them was 2 degrees. Could you find the arc length, in other words, the S that actually differentiates these two? Well, the first thing we would need to do on this particular problem is we would want to change this 2 degrees into radians. So how do I go about changing degrees into radians? Well, the easiest way is to remember that there are 2 pi radians in 360 degrees. That's usually the easiest way I do it. Now, a lot of people will say, well, I know that there's pi over 2 radians in 90 degrees, or that pi over 3 radians is 60 degrees. So you can remember some of those, but it's always easy to kind of go through the full circle, and I think you'll be fine. So when I actually multiply this out, basically what I'm going to want to do is I actually want to get a number for this. I don't want to just leave it in terms of degrees or pi. I actually don't want to leave it in pi. So I'm going to go 2 times pi times 2, and then I'm going to divide that by 360, and I get this to be 0.0349 radians. 0.349 radians. That is going to equal my arc length divided by my radius. So if I want to actually find the arc length, in other words, the actual distance between these two satellites, I would just take this 0.349 radians, actually 0.0349, sorry about that, 0 radians, and multiply by the radius. So I'd multiply by that radius, which is this number up here, 4.23 times 10 to the 7th meters. Now, the radian actually doesn't it's it's a weird unit. It's a unitless unit. So when you actually multiply, we don't get radian meters or meter radians. We just kind of drop the radian and we just are going to end up with meters. So if I multiply this by 4.23 times 10 to the 7th, I get that it would be 1.47 times 10 to the 6th. Actually, 48 times 10 to the 6 meters. Ta-da! Just a little bit of idea with angular displacement. Taking a look, let's see, they got the same thing here. And look at that. They changed it into miles, but we didn't need to. So everything that we've got. So I'm going to finish with this one, which I think is kind of a cool idea. So I'm going to move me out of the way just for a second. If you're familiar with the total eclipse of the sun, we know that when the moon is in between the sun and us, it will actually completely block out the sun. We experienced this a few years ago. We're going to experience it again in 2024. We're going to be able to actually see it here in our area again, which is going to be awesome. It'll actually be in April, which will be kind of nice as well. So I'm hoping for good weather on that day. Um, why is that? Why do they actually overlap? So what I want to leave you with is this idea is if these are the information about the sun and the moon, what do you think is true about the angle that each one is going to subtend is what it's called. So in other words, if you were to actually figure out this little angle that's looking at the moon, how big of an angle is it? Noticing the distance, or the sun, how big of an angle does it actually, if we think of it as kind of a curve out there as kind of an arc length? And you'll be amazed. So I give you some information. I have some meters here, I have some miles. If you just kind of do a cursory one, you'll notice something very interesting right away about the ratio of the diameter, which would be your arc length, over the radius, which is going to be the average distance to those planets. So I'll leave that as kind of a question for you to finish out in the Google Form notes. Hope you enjoyed this little video on angular displacement. Take care.